differentiation problems involving the definite integral. The definite integral has meaning, and that's where we're going. Irene, take it away.
In the swimming pool problem, our initial function R of t had units of gallon per minute and represented the rate at which water was leaking through the pool in gallons per minute. The definite integral from t equals 0 to t equals 8 R of t and V of t was used to determine the total number of gallons that leaked from the pool during the time interval t equals 0 to t equals 8 minutes.
Okay, so stop right there. I wanna decorate this a little bit. What did R of t represent in that swimming pool problem? It was a rate, right? It represented how fast. How fast what was happening? How fast the water was leaking. And that had units, I think the units were gallons per minute according to what Irene read to us. R of t, the function itself, was a rate function. When you work with rates, we're going to use words like how fast, how slow, not how much, but how quickly things are happening. The units for R of t, you guys just told me, were gallons per minute. And the units for the time were minutes. If I've got gallons per minute for the units for R of t, and minutes as the units for the dt, what are the units for the whole thing going to have to be? Not gallons per minute squared. Gallons. You've got minutes in the denominator, minutes in the numerator. This is just going to be gallons. R of t is how fast the water is coming out, but the definite integral from 0 to 8 is going to represent how much. So not how fast now, but how much water leaked from t equals 0 to t equals 8 minutes. When you're dealing with a rate function, your units are going to be like something per something, gallons per minute. The amusement park problem, I'm going to pass back to you guys, the units were something like people per hour, right? So if my rate function is gallons per minute and I'm measuring time in minutes, then my definite integral represents a total of how much, not how fast. We're okay? All right, so let's move on. Fabrizio, can you read the second paragraph?
In physics, v of t, the velocity, is a measure of the rate at which position changes, and the fundamental theorem.
Wait, is in physics, v of t, the velocity is a measure of the rate at which position changes and the definite integral?
Oh yeah, the definite represents the total change in position from t equals a to t equals b, otherwise known as displacement. If v of t is measured in centimeters per second and time is measured in seconds, then definite integral will be measured in length.
So what am I going to measure that at? V of t, what are the units?
Centimeters per minute.
Well, oh, golly, some people are still like flashing back to gallons here. V of t
Centimeters per second.
is centimeters per second, and the time is measured in seconds. Seconds in the denominator, seconds in the numerator. My units are going to be
Centimeters.
centimeters. Now V of t, you guys know V of t stands for velocity, but it is a rate. It is a rate. It is telling you how fast what?
How fast
Velocity.
The position.
changes.
How fast the position changes. So look at this. It's another how fast rate. If v of t tells me how fast the position changes, then my definite integral is going to tell me how much the position changes. My definite integral is a measure of how much the position changes. How much the position changes from t equals a to t equals b. You can write that. That is a perfect explanation. If the function is a rate, it's a how fast, the definite integral is always going to be a how much kind of explanation. Now, for those of you that are like, I don't want to write how much the position changes, because we have a better word for how much the position changes. The better word is
Displacement.
displacement, right? We're gonna say, what is the displacement from t equals a to t equals b? Everybody mostly okay? Your rate functions are gonna be about how fast, but the definite integral is always gonna be a question of how much. So while I take attendance, I want you guys to read through example 1, like you would if this was on the quiz on Friday. Read through it, mark it up. If you want to take out your calculator and get started on it, great. 2 minutes from now, we're going to talk. We'll have some good conversation. I'll take any questions that anybody has. But 2 minutes of independent work here. Josue, how do you feel about driving again?
Huh?
Are you okay with driving over here? Will you be my smart board?
I'm taking my job again.
You're taking your job?
Yeah.
Okay.
Ooh.
Nice. Okay. It's all yours. All right, friends, what's happening in this problem? Brand new situation, we haven't dealt with this before. Alejandro, what's happening in this situation?
The coffee is cooling down from 10 to 0 to 10.
Okay, so we've got a cup of coffee. The initial temperature of the coffee?
90.
90 degrees. I'm gonna put it into a room. Think about this for a second. Forget about calculus just for a moment. Salma, what happens to the coffee? It cools down, right? It has to cool down. It starts off at 90 degrees Celsius and it cools down. Now, I'm curious. Will the temperature of the coffee ever get to be 0 degrees Celsius?
No.
Will the temperature get to be 0?
No.
Why not?
Because like when the temperature is decreasing, it's going to the room temp. It's going to match the room temperature.
Right, if the temperature starts off at 90 degrees Celsius, it's going to cool, but it doesn't cool forever, right? We're not going to get ice in the coffee. You're going to start at 90 degrees Celsius, and you said it's going to cool until...
Until it reaches room temperature.
Is everybody okay with that? Now, so if I think about the graph of what the graph of temperature should look like, this is not part of the question, but here's time, here's temperature. At time 0, you guys already told me I'm going to start off at 90 degrees. And what happens?
It is like this.
It goes like down like this? Like that?
Yeah.
Oh, I was hoping everyone was going to say no. Because that contradicts what you just said.
But it makes sense.
Abel, what's the problem with what I drew?
Well, since you said it's gonna, what did you say, increase, but it would be like sort of increasing because you're changing the temperature, but it wouldn't be, it wouldn't start at the top, it would start at the bottom.
But hold on, we're looking at time versus temperature. And at time 0, the temperature does start off at 90 degrees. And what happens?
It starts to go down.
Won't the temperature have to decrease? What I drew was that. Why not that? Why not that graph? Of all the things I could possibly draw, why not that graph, Salma?
Because that one doesn't, that one's reaching 0.
That one's, I wouldn't say reaching. Reaching's not the word. Approaching. The temperature is getting closer and closer to zero. And what Janaea already told us is, we're not gonna reach zero. What's gonna happen?
And approaches.
It gets to room temperature. And what's the temperature of the room?
20 degrees.
20 degrees. So if here's 20 degrees Celsius, and I draw my little line there, my graph technically should look like that. Always a little bit above room temperature. For those of you that really loved chemistry, and there may not be a lot of folks in the room who loved chemistry, don't worry, I won't tell Miss Nina. Oh, you guys didn't have Nina for chemistry?
No.
Gainer, okay. If the temperature of the coffee is 90 degrees Celsius and the temperature of the room is 20, the coffee is always going to be a little bit warmer than the coffee, because the energy from the coffee gets transferred to the room. And so you kind of reach this equilibrium point. But that's what your graph is going to look like, theoretically. All right, part A. Here's what I'm really interested in. Not a number, but a meaning. The number's coming later. We're going to get a whole lot of practice with the calculator. What would this mean? The definite integral from 0 to 10 r of t dt. I see Alejandro again. I see Jasmine. Jasmine, give it a shot.
It is how much the temperature has decreased from T equals 0 to T equals 10.
Did everybody just hear what she said? It's how much the temperature has decreased from T equals 0 to T equals 10. How many guys would agree? We got some folks? If you're not 100% sure, go back to R of T. What does R of T represent?
Rate.
It's how fast the temperature did what? Okay, don't use changes if you can be more specific. Don't tell me changes if the right word is decrease. How fast the temperature decreased, the definite integral is going to be how much the temperature decreased. How much the temperature decreased from when to when?
T equals 0 to T equals 10.
Okay, it's those limits of integration from T equals 0 to T equals 10. And if I said, what are the units? What are the units for the change? For the change in temperature. This is going to have to be degrees Celsius. If you're not sure, go back to R of T. R of T is measured in degrees Celsius per minute. My temperature is being measured in minutes. Those guys cross off. It should all fit together. We're okay? I care a lot about your ability to explain the big idea. And now what I want to do is give you guys some practice with the calculator skills. So part B, using your calculator, determine the exact value of the integral from 0 to 10 r of t dt. Round your answer. I'm going to put about 6 minutes on the clock. I want you guys to go as far as you can with B, C, and D. When you're ready to check in with me, let me know. Why, hello. I was having nightmares about you two just the other day. You're out of prison. Good job. Keep going. They're in college. You want to get in so that you can date men like this someday. See you later. When you think you've got part B, show it to me. I want to do the happy dance around you. See, I like it, don't love it. Like it, don't love it. What you got? Like it, don't love it. I got a whole lot of people not reading the instructions. Not quite. You are going total big brain, which is really good, but read this question. All I want to know is what's the value of 0 to 10. You're answering a different question. You want to get it out of my bag? Perfect.
That's what happy dance.
Full points for Cassandra. Keep going.
Is it
I guess the main. I went to, I put 0, 10, and that's what I remember.
You already got it. I know.
Okay.
You already got it.
Yeah.
Okay. Did you put the green?
Love it. Be careful. I always want 3 decimal places except when I don't. Nice. Keep going. Love it. Oh my God, you almost poked me in the belly. Love. Love. Almost loving. Not centimeters. You're measuring temperature change. Okay. Most popular wrong answer is up here on the board right now. Most popular wrong answer, negative 44.248 degrees Celsius. Claudia, do you know why that's the wrong answer?
We need a whole number.
Because you need a whole number. Why do you need a whole number? Because it says in the problem to round. I always want 3 decimal places of accuracy, except when I tell you otherwise. Negative 44 degrees Celsius. Keep going. Part C, lots of fun here. Good times.
But it's using the right format.
Whenever you're using a sum, you can always use it around.
So close. So close.
I mean, find the flow. Wait, no, I'm thinking of it. Is this one? The limit. I'm just like pushing on it.
Oh, yeah.
I know I'm part B. Part B infinite. No, that is the value. And remember, we need to find, and minus equals that and then we use a triangle method. 10 over 10. Where did you get 10 from?
Much better. Keep going.
The one who said,
Close. Yep. Keep going.
No, hold.
So close. Alrighty. If I've already given you the thumbs up on part C, keep going. Keep going. But I want to talk to anybody who's maybe not doing 100% well on part C. So where are those folks? Okay. So I want to know infinitely many rectangles, right? And I'm really restricting myself here when we do these right rectangles to be on the right endpoint method for reasons that we'll talk about someday, but it's not today. Usually the way we're gonna start is you start with n rectangles. And if I wanna go from 0 all the way to 10 with n rectangles, I make my little partitions. The first question that I'm always gonna ask myself is, how wide's each rectangle? How wide's each rectangle? I'm only interested in the folks that are struggling with this. Salma, how wide's each rectangle?
10 over n,
How'd you get that?
because there's 10, you have to go to 10?
You have to go from 0 to 10.
Yeah, and.
So 10 minus 0 divided by n. So 10 over n, that's going to be the width. That means my first rectangle starts at 0, and where does it end? At 10 over n. But then to get to the next rectangle, I move 10 over n again. So now I've got 10 over n times 2. The next one is 10 over n times 3, 10 over n times 4. I'm going to keep moving 10 over n spaces until I get to the last one. And is that last one correct? 10 over n times n. Does that get me to the last rectangle? 10 over n times n, the n's would cancel, I get to 10. Right, there's some graph that we're thinking about. Here's r of t, and I want the right endpoint method. So from 0 to 10 over n, go up, over, down. Next one, up, over, down, up, over, down. 1, 2, 3, keep on going till you hit your last rectangle. That's the nth rectangle. For the folks that are with me, tell me about the first rectangle. Alejandro, tell me about this first rectangle.
Would it be R 10 over n times
So 10 over n is the width of the first rectangle. How tall?
R
R of, if it's the right endpoint method, I use the right endpoint, so it has to be
10 over n.
R of 10 over n? Okay. Somebody not Alejandro who's still with me, tell me about the second rectangle. How wide, how tall? Cassandra?
10 over n,
10 over n is still that width, right? How tall?
r, 10 over n times 2.
R of 10 over n times 2, that's the second one. Salma, tell me about the third one.
10 over n
10 over n.
times r, 10 over n times 3.
Okay, and I'm gonna keep on going until I get to the last rectangle, which is 10 over n times r of 10 over n times n. Okay, then we start looking for a pattern. What's the pattern? Juan, what's the pattern?
The 10 over n.
Okay, every one of these terms has a width of 10 over n. What else? What else is going on here? Fabricio, what else?
Addition.
Okay, they're all being added together, and so the nice way to compact all of that,
Or like
no, there's that notation that I'm really interested in here.
sigma.
The big sigma tells me I'm going to go from I equals 1 to n because there's n rectangles. Each one of these area calculations has a width of 10 over n. They're all r of something. 10 over n, 10 over n times 2, 10 over n times 3, so on and so on, 10 over n times I like it, I don't love it. The most important piece that we haven't tackled yet, you need to know that what we're doing is a limit as n approaches infinitely many rectangles. How many of you guys honestly had this as your setup? I'm curious, how many of you all are able to go from the original setup straight here? That's a good thing, right? You've seen the pattern. If you don't have to go through all of the development every single time, please don't. Big mistake that I see a lot of folks are forgetting to include that little r there. I saw a lot of folks that had 10 over n times I. You're evaluating the function at 10 over n times I. Okay? All right, let's skip over part D because I want to pull everybody back together. Let's do E, F, and G. E and F, we need some big brain thinking here. big brain thinking. There's a little idea that I'm planting a seed right now so that it waters, but I'm not gonna tell you the name for it yet. Well, I'm just watering the seed. Part E, have a conversation with somebody about this. Determine the temperature of the coffee at T equals 10. What would you do? How would you find the temperature of the coffee?
Then I guess I would expect that I can have the same. But I don't know.
But if this is RT,
So what's the actual temperature at T equals 10? So far, the answers I've seen, what did I see? I saw R of 10. I've seen 90 minus R of 10. And I've seen the integral from 0 to 10, R of T dt. Each one of those three is wrong for completely different reasons. Anybody want to tell me why any one of these three is wrong? Brianna, tell me one.
Because we not trying to find the rate of which the coffee's temperature is changing.
Right. R of 10, R is telling you how fast or how much?
How much?
Oh, no. It's a how fast. So R of 10 is how fast the temperature changes, not what is the temperature. Get that one out of there. Popular one, integral from 0 to 10 R of T dt. Why not this one? Just Jasmine? Why not this one? I see Brianna, I see Janaea. Cassandra, why not this one?
because it will give us like how much the temperature decreased.
How much the temperature decreased by. What I want is what is the actual temperature. The person over here is telling me this. What they're actually going to tell me is how much the temperature decreased by. But I'll tell you they're close. They are so close. So close. Abel, what do you got for me?
It would be 90 minus the definite integral from 0 to 10, and then R of t times dt.
Okay, so I hear you saying 90 minus the definite integral from 0 to 10 R of t dt. The significance of the 90? That was the initial temperature. That's what you started at, right? Now I hear minus the definite integral from 0 to 10 R of t dt. Go find that number for me. And someone will tell me what's wrong. Someone will tell me what's wrong. In just a moment, Abel. Someone will tell me what's wrong. 90 minus the definite integral from 0 to 10 R of t dt. There's a really good reason why this is wrong. And once you see it on the calculator, you'll know why it's wrong. $90 minus the integral from 0 to 10 f1 of x dx. According to Josue's calculations, the temperature of the coffee is now a scolding 134.248 degrees. It started off at 90 degrees. You put it in a room at 20 degrees Celsius. 10 minutes later, it has cooked. You put it in a microwave oven that pretended to be a room. Salma, what's the mistake?
You're not supposed to subtract by negative, you're supposed to subtract by the positive, by the absolute value of the integral.
Whoa, okay. I like where you're going there. You had me when you said don't subtract. This guy over here is already telling me a decrease. If you say 90 minus the decrease, what you're actually doing is you're adding on to the temperature. So if this already represents a decrease,
Yeah.
how about 90 plus? It's the initial temperature plus the total change. And if you try 90 plus the total change, according to Josue, now we're getting 45.751 degrees Celsius. Let's label this. That 90, what does that represent?
The initial temperature.
Right, this is like initial temperature or temperature at time t equals 0.
I got 46.
You got 46? No, it should be 90 plus the integral from 0 to 10.
Correct? 'Cause I messed up on
Yeah,
it.
you may have checked the function in wrong.
I put
I just
0.11.
put negative 44.
Oh, because you rounded from before? You want to do the calculation again? The 90, everybody's okay, this is the initial temperature? This guy here, the definite integral?
How much?
Right, this is like how much temperature decreased by, and this last one,
The current?
or like the final temperature. Your initial temperature plus the change. So awkward. Initial temperature plus the total change gives me the final temperature. Okay, with that in mind, one last one. Show me what you guys can do with part F. Set up but do not solve. You cannot give me a number here. I want an equation that you would use to figure out when the temperature is going to be 30 degrees. When is that temperature actually going to be 30 degrees? Okay, so here are some of the things I've seen so far. I've seen the definite integral from 0 to 10 r of t dt is equal to 30 degrees Celsius. I've seen the integral from 0 to t r of t dt is equal to 30 degrees Celsius. Neither one of those is right. Somebody tell me why. Take one of them. What's wrong? I'll take anything from anybody. Melissa, what do you think?
I thought the 90 was supposed to be added.
Okay, so you think we need to do something with 90 here. So you want to do something with 90. 90, what would you do with the 90?
90 plus the definite integral.
90 plus the definite integral from where to where?
0 to
T,
R
r of t dt, and then, is that it?
no.
Okay, we've got 3 different ideas going on here, possibly even more than this. No one's 100% right yet, that's okay, it's meant to be tough. Can anybody point out anything that's wrong with any one of these 3? Cynthia, something that you know is wrong.
Okay, for the first one, it's saying that at 10 minutes, the coffee, whatever,
Yep.
is 30 Celsius.
Actually, that's not what this would tell us.
Oh, the,
What this guy over here, the definite integral, is telling you how much the temperature changed by.
So it changed with it.
So what this person's saying is from 0 to 10, the temperature changed by 30 degrees. Is that true? No, we know that's not true. So get that one out of there. Other things that we know are wrong. Salma, what else you know is wrong?
I have another one,
Or you got another one you want to throw up here?
yeah, 90
90,
plus the integral from 0 to 10,
0 to 10.
yeah, R of t dt equals 30.
Equals 30. Okay, now we have 4 that have some issues. Alejandro,
For the second one,
this one?
since we need to find when the cup of coffee is 30 degrees Celsius, it needs to be equal 60 degrees Celsius because that's how much it has changed.
Okay, so I hear Alejandro, you're saying get that 30 out of there and put 60 because the 60 is supposed to represent the change. How do we feel about this one now? How many guys would agree with this one? Alejandro. Only Alejandro.
I'll do them.
Brianna wants to go?
Yeah, I'll do them.
Okay.
They won't be allowed. So,
Still not right. Close. So close. What's wrong with that?
90?
the 90, the T, 90
What's wrong with this one?
There's no range.
The integral from 0 to t is going to tell you how much the temperature of the coffee changed by, right? This version saying the temperature of the coffee has changed by 60 degrees, changed by a positive 60 degrees. You're asking me when is the temperature of the coffee 60 degrees more than it was before? So how about negative? Because R of t is how fast the temperature decreases. The integral from 0 to t is going to be how much the temperature of the coffee decreases by. So this one would work. The one I was hoping for looked a lot like this guy here. Melissa had great instincts. The 90 is your starting temperature. I needed to start at 90 degrees. 90 degrees plus the total change has to be equal to, what's the final temperature? The initial plus the total change has to be equal to 30. And that would have worked. And it's the same thing as this guy over here. If you subtract 90 degrees from both sides, 30 minus 90 is going to be negative 60 degrees. I would take either one. What's wrong here is you think you're ending at 10 minutes, and the issue is we don't know when we're actually ending. It could be at any particular time. So don't pick this one. Now, you guys know I like to wear the picky pants. Love to wear the picky pants. There is one small thing wrong with both of these. And it's not something we've ever talked about before, so I want to make sure this comes through loud and clear. The College Board would say, like it, don't love it, because you're using the variable t in here as your variable of integration, and you're using it out here as a limit of integration. You don't want to overuse the variable. Use it in one place, use it in only one place. And the place that you need to use it, if you go back to the question, they wanted to know at what time do you stop, like at what time is the temperature 30 degrees? So use the t here, don't use it in here.
So we can change those to another variable?
So the question is, what do you use? If you can't use t, use anything else. If you're Brianna, R of B, dB. If you're in the X-Men, R of X, dx. Don't use t. Please, baby, please, don't confuse all of us and use R. And don't use D. You want to impress the ladies or the other soccer players on the field, R of theta, D theta. I don't care. But don't use the same variable as your limit and in the integram. Cassandra.
I don't understand where the 60 came from.
Okay, we can talk about that in a little bit. Here's what I want to do. We've got a little bit less than 10 minutes left. Tonight's homework, you guys already know, is to finish up the application problems.
Yes.
What I want you guys to do in the next 5 minutes, show me what you can do with these 3 sample AP questions on page 3. Find one person, but only one person that you're going to commit to working with.